So we're talking about rotation about fixed axis, right? I brought the last slide or last two slides, I would say, just to refresh your memory about what we were talking about. We said, well, motion in motion of a rigid body, you can look at it as, at least in a 2D plane, you can look at it as three types of motion. It's either translation. Translation, we say, is pretty straightforward. The motion or the velocity and acceleration of all the particles on a rigid body are the same. So there is not that much to talk about there. We have rotation of the fixed axis, which that's what we talked about in the last class. Then we have also the general planar motion, which is a combination of translation and rotation. That's how we can look at it. Now, we went over rotation over the fixed axis over one example, I think. Well, I talked about it. As I said, there is nothing really fundamentally new there. The whole idea is that, well, every point on a rigid body, you can look at it as a point that we were studying before when we were studying rotation or motion on a curvilinear path, right? And so here you can use tangential and normal coordinate system, because basically in a rotation over the fixed axis, every point on a rigid body is going on a circular path about the axis of rotation, which in two-dimensional space is basically just a point in the plane. And we talked about a special case, two gears, when they're engaged, when one rotates with some specific velocity and acceleration, you can find the relationship between, or better to say, you can find the relationship between velocity and acceleration between the two gears that are engaged. There's no slipping there. And we specifically said at the point of contact, velocities are the same. And from there, we could find the relationship between angular velocity and angular acceleration for two gears that are engaged. Then I went over one example. We went over this one. I'll go over one or two more examples, and I post another one or two examples for this topic, then move on to general planar motion. Look at how things work and how can we actually study rigid body motion in a plane in a general form. Right? It's not just rotation over the fixed axis. Rotation over the fixed axis is a special case for translation, and rotation over the fixed axis, both are special cases for the general planar motion. All right. Let's look at this example. I do have a figure somewhere. I think it's 2.2. Yes. Relatively straightforward, just again to solidify what we have learned and what we saw for rotation about the fixed axis, right? We have two gears. At this moment, I'll call this left gear and call this right gear, L and R. Left gear is moving with the angular velocity 3 radian per second counterclockwise, and also its acceleration is 1 radian per second squared clockwise. We know its radius 1 meter. Right gear, we know its radius 2.5, and also there is this point A, which is 2 meters away from the axis of rotation. All right. So what we want to find, A, is, given all this information you have here, part A is asking you to find what are the angular velocity and angular acceleration of the right disk, if I can. Right disk, there you go. Right. And obviously you can assume that there is no slipping, as we said in this course. At least we don't really talk about slipping between gears, so there is no relative motion between the disk on the left and disk on the right. I keep referring to these as gears, but the problem actually is saying these are like discs. So gears, it's easier to think about them as gears because there is no slipping. Discs, since we mentioned disc, maybe I should add that there is no slipping between the discs. All right. All right. So this is basically a direct implementation of the special case that we talked about, right? We said when we have two gears, in this case, there are two discs. There is no slipping or no relative motion between these two discs. So we can easily use what we derived from before, right? We said that at point of contact, velocities are equal. As a result, we can just say RL. So I can write it this way. I'll go to part B. Let's just finish part A and then we'll look at part B. RL omega L is equal to R right omega R for the right disk. We know the velocity, so here is omega L, this is alpha L, and this is RL, right? The radius of left disk, and this is R right, radius of the right disk. So the only thing unknown here is the angular velocity of the disk on the right, or right disk. So omega R would be RL omega L over R, and just plugging in the values, that becomes 3. Or we can just write them as well. RL is 1. Omega L is 3 divided by R right is 2.5. Like with 3 over 2.5 becomes 1.2. 1.2 rad per second. All right. That's the velocity, angular velocity of the right disk. Angular acceleration, again, direct implementation of what we got there, right? That's better to say to start from here. RA alpha A is equal to RB alpha B for two gears that are engaged, gears A and B that are engaged. Here we have left and right. So R L alpha L is equal to R right alpha right. From there, you can find alpha R. That would be RL alpha L divided by R. RL is 1. Acceleration of the left disk is 1. Radius of the right disk is 2.5. So that becomes 1 over 2.5. That's 0.4, right? Radian per second squared. There you go. All right, that's again, it was just an example just to practice the equations. Pretty straightforward, I think. Now, part B is telling us to find the magnitude of velocity at an acceleration at point A, right? This is point A, right here. It's 2 meters away from the axis of rotation, right? The rotation is happening if this, if the left disk is rotating counterclockwise, so the right disk is rotating clockwise, right? This is omega R. Right? If this is going in this direction, this is going in this direction. Angular velocity. Acceleration is in the opposite direction. It means that left disk is slowing down, right? It goes in this direction with 3 radian per second, but the acceleration is in the opposite direction. So after some time, it just is going to stop. Right? It's going to reverse probably if the acceleration stays in the same value in the same direction. Set at the specific instant that we have this. It might change later on. Right? They're not given any information about that. All right. So part B says, what are the magnitude or magnitudes of the velocity and acceleration of point A. All right. So as I said before, this is like similar to what we were studying before when we had a point rotating about some axis, right? When we were looking at all the way beginning of the semester, when we were looking at motion of particles or points, when we had a point rotating about an axis, right? That's what's happening with point A, right? Point A, when the right disk is rotating clockwise, point A is basically following this path, right? It goes around the center, right? This axis of rotation in the middle. So V, if you think about it this way, V would be tangential to path. This is going to be your V, right? That would be your VA. And your VA is RA omega of the disk, because it's rotating with the disk. So RA it's 2 meters away from the axis of rotation or center of rotation. Omega R, we found it the previous part section or part is 1.2. So this becomes 2.4 meter per second. Right, that's the magnitude of velocity, and it's in this direction. Now for the acceleration, right? Let me draw this here. If we have point A right there, and then this is the center. For the acceleration, you get two components. One is tangential component, one is normal component. So that becomes a t, this is a n, given that this is et and this is en, right? Tangent normal coordinate. So acceleration as a vector is, all of these are vectors, is acceleration, whatever it is in tangential. I write it this way: a acceleration of point A tangential et plus acceleration of a normal en. Now, whatever is the acceleration tangential direction times et, whatever is acceleration normal direction times en in this coordinate tangent normal coordinate system. And separately, we can look at them. Again, goes back to what we studied at the beginning of the semester. Right? We said a tangent is r alpha, so RA alpha over the right disk. And normal acceleration is R A omega R squared, right? Omega with which the point is moving, which is basically the same as the omega of the right disk squared. So RA is 2, alpha R is 0.4, so it becomes 0.8 meter per second squared. RA is 2, omega R we found as 1.2 squared. That I don't know, it becomes 2.8, 2.88 meter per second squared. And you're asked to find the magnitude of acceleration. So the magnitude of acceleration is the square root of whatever is the tangential component squared plus whatever is the normal component squared. 0.8 squared plus 2.88 squared, you'll get 2.99 meter per second squared. That becomes the magnitude of the acceleration. This was the magnitude of velocity. right? So very similar to what we were doing before when we were looking at the motion of a point or a particle in a circular path. Right? Just in this case, that point is part of the rigid body rotating about the axis. All right. Question on this one, guys. Pretty good. I'll wait a little bit. You're right, you know. All right. So one more example, and I just want to say that with that example, I'll just want to emphasize that the object rotating about a fixed axis does not have to be a disk, right? In both cases here, we looked at a pulley. In this case, the second example, we looked at two disks rotating. There's a point of contact here, and at the same velocity at this point. We use that to find the angular velocity acceleration for the other disk once we knew them for the first disk or disk on the left. Now, it doesn't have to be a disk, right? As long as you have a rigid body rotating about an axis, right? You should be able to use rotation about a fixed axis, whatever we derived here, the equations here, and we should be able to study that motion. So here is the next example. What figure is that? I think it's 4.2. There. We have this bar, right? And it's rotating around this point right here. You can think about this point O. It's like the center of rotation. When three-dimensional is an axis, right? Either going to the screen or coming out of the screen, depends on which direction you take as positive or negative. So this is with all these dimensions, and the problem statement is telling us that if the bar, if the bar is, or where to say it this way, has a counterclockwise angular velocity of 8 rad per second, so counterclockwise 8 radian per second, it's pretty much rotating in this way, right? 8 rad per second. What are, I think that's pretty much it. I know. And you need the angular acceleration. And clockwise angular acceleration of 40 rad per second squared. So clockwise, this is 40 rad per second squared. Right. We are asked what are the magnitudes of acceleration of points A and B. All right, so point A is top left, point B is top right, bottom right. All right, so you probably can see that both points are rotating on a circular path because they're part of the rigid body rotating about an axis, right? So if you think about point A, if you're rotating counterclockwise, point A is following a path like this, right? This, I'll just don't continue because I can't really make it circular, but circular path. and point B is following a path like this. Not exactly the best circular path, but you get the idea. So we want to find the acceleration. Let's just start with point A. We want to find the acceleration of point A. Now, if it's rotating on a circular path, let me give it another try. Let's say this is a circular path that we have there. Right? And well, let's go with this as the radius. It's happening around point A, point O, rotation. So let's write the equation. So acceleration of point A is, and we can put the coordinate there. This would be the tangent direction. This would be the normal direction. ET, EN. You can see how crooked my path has been. So let me try make it a little better. So this becomes a tangential component. Right. So A has two components for part A. For point A, AT ET plus AN EN. All right, now for AT, you'll get R A alpha, alpha for the whole disk. So just for the whole bar. So put this alpha, and I call this omega. So I don't put it specifically for point A. Every point on this bar has the same angular velocity and angular acceleration. Right? They're part of the same rigid body. And AN would be R A omega squared. Now we know alpha and omega. We don't know RA, which is this distance, RA. But this is a right triangle, so we can find RA. So I can say RA is the square root of 0.4 squared plus 0.4 squared. This becomes, well, I have to look at the answers. This becomes 0.565 meter. Right. Once you know RA, you can actually plug that back in this set of equations. RA is 0.565 multiplied by alpha, which is 40. Right. That gives you angular the acceleration, tangential component of the acceleration. Normal component of acceleration is 565. 565. And omega is 8, so 8 squared. Right? From there, we can actually find the values. For the first one, you'll get 22.62, and would be meter per second squared. For the second one, you get 36.2 meter per second squared. So once you know, this is 627. Once you know the components, you can find the magnitude. Magnitude of acceleration for point A is basically the square root, right? AA tangent squared plus AA normal squared. You do the math there, you'll get 42.69 meter per second squared. Right, the acceleration of point A. Of point A. All right. Any question on this one, guys? All right. So same story for point B, right? For point B, we have, if this is B, let me draw this line here.
Guys, I have a quick question.
Go ahead.
So does the angular velocity rotating counterclockwise not change the sign at all? Like it doesn't matter?
Oh, actually, it's a good point. I had to thank you for pointing it out. This should be in this direction, because we always go with the direction of the rotation, right? I was not paying attention. Does that solve the issue there? Or was that what was causing the problem?
Yes, then wouldn't alpha be negative in this case? Or no?
No. So when we look at it in two-dimensional space, right? We always take the direction of normal towards the point that we have the rotation about, right? And in three-dimensional space, yes, alpha is negative, right? But what you get in this two-dimensional space, you're fine with just following this notation. If we were looking at it in three-dimensional space, the axis would be a little, the whole story would be a little different. But in this case, doesn't really matter. If it makes sense. Yeah.
Okay.
Yeah. But yeah, in a sense, it is negative. If we take this ET in this direction, then this would be negative. Now I'm doubting maybe it would have been better if I just kept it the other way, because then we could argue that it's positive. Because if you keep it this way, just to make it more confusing for you guys, and if it wasn't enough, if you keep it this way, you can argue that it's actually positive alpha, because in that tangent in this coordinate system, right, E, T, E, N, then the third axis would have been going from tangent to normal, would have been going towards the screen. I'll show it this way, like the back of an arrow. It's going towards the screen, and then alpha would have been in that direction. But let's not get into that the third dimensional argument. But just to answer your question, if I take ET in the other direction, alpha would have been negative. If I take ET in this direction, alpha would be positive. I'll just put it back to where it was. So we follow our own notation in this course. So take tangential in the direction of the motion. So just keep it in this way. Since we don't really talk about three-dimensional problems, we don't really get into these, which is a good thing, I guess. All right, so for point B, the same story. Right? All you have to find is where B is, if this is RB, right? And then this is the path that point B, let's say, follows in this motion. You can again come up with your tangent normal coordinate system. All right, this is ET, this is EN, and then I didn't really draw the pathway best way possible, but it's a circular path. So get the same story. AB is equal to AB tangent E tangent plus AB normal E normal. Then AB tangent would be RB alpha. Well, alpha is the same for the whole rigid body. And AB normal would be RB omega squared. You have to find RB. So RB is again in this right triangle. You have the square root of 0.4 squared plus this height that I kind of covered. It is 0.2 squared. So that'll be 0.447 meters. Right? Once you have that, then these two are just plugging in the values. 0.447 multiplied by alpha, which is 40, and then RB, which is 0.447 multiplied omega, which is 8 squared. You do the math there, you'll get, for the first one, you'll get 17.88 meter per second squared. For the second one, you will get 28.62 meter per second squared. So your magnitude, the magnitude of the acceleration, or same story, AB tangent squared plus AB normal squared. Like once you have two components in the coordinate system, just the square root of the squared of summation of the squared of both, you'll get 33.75 meter per second squared. All right. So this becomes the acceleration of point B. Acceleration of point B. Any other point, as long as you can find how far is that from the axis of rotation, you can just find its velocity and acceleration. So all you need to do is just, you need to know the angular acceleration, angular velocity of the rigid body. Any point on that, you can calculate depending on how far is that from this axis of rotation. This could go the other way around. They could give you the magnitude of acceleration and velocity, and they could ask you to find other components. But I'll post that as an extra exam practice problem you can look into. And also there is another problem I can post as an extra practice. I'll post two extra problems for your practice aside from the examples event through in class. Now, what I want to start talking about is the general motion, right? So rotation over the fixed axis is relatively straightforward. Hopefully you see it the same way I see it. Now, things get a little more challenging, I would say, when we start looking into, I don't know why did I stop sharing my screen. All right. When we start looking into general planar motion, right? And general planar motion, by that I mean when your rigid body is not bound to be fixed at some point and just to rotate around that point or axis, right? Here we're talking about the rigid body that can move in a plane. And again, we don't really cover three-dimensional problems, 3D problems in this course. Now, how do we deal with that? Well, let's go to the next page. So I want to talk about general planar motion. General planar motion. And since I think it's better to separate velocity and acceleration, let's talk about the velocity first. Get comfortable with velocity. Then we'll bring in the acceleration and see how to deal with acceleration and the components of acceleration. So let's put velocity, right? So we said that when we have translation, or we said we can have translation, we have a kind of rotation over the fixed axis and general motion in two-dimensional space, right? I brought that figure of that engine. Car engine, we looked at all three possible motions that basically happens in a you can see that in a car engine. So in translation, each point of the body we said basically has the same motion, right? If it translates this way, and every point on this rigid body goes with the same velocity and acceleration. In rotation, right? We talked about rotation, so I don't go there. Now, general planar motion, you can think of it as a combination of both, right? Let's just write it this way. So you have translation plus rotation. So you have something that is translating and is rotating at the same time, right? Going from one place to another. Or it's just on the same plane. So you'll be, you'll be having the general motion that you see in a rigid body in two-dimensional space. Now, how do we deal with that? Things get tricky. So I want you to be very focused for the next, how much left is the class? Half an hour, right? If you listen, I think it makes sense if you follow. But if you get lost and you do not follow later on, you'll find a lot of points that think a lot of situations that just it seems confusing. So please, if you were not very focused on what you were doing, be more focused at this point. All right. Now, the way we solve the general planar motion is that we need to define coordinate frames. Again, that's the whole new thing that the relative motion comes into play. We didn't really exactly talk about relative motion, but that's where we talk about it and how it helps us to study general planar motion. Right? So let me put it this way. When we have this, we need to define a coordinate frame. Coordinate frames. So here I'll say, and wanted to mention that the way I solve these problems, it's basically a scalar approach, meaning that we have the vector, and then you'll see we decompose the vector into its components, so we get two sets of equations. One, because the vector has magnitude and direction, right? So we get two sets of equations, we can solve them. In your textbook, I think the general approach is using vector notation and doing the whole cross product. I personally am not a big fan of it, but I will give you enough solved examples using scalar approach that you will be totally comfortable, or you will be fine with the approach I follow. But if you find the way this textbook solves the problems easier, by all means, feel free to do that. You should get the same things. You will see the only difference is that you do a little bit more math, basically doing the cross product. What we do in this approach, in the scalar approach, we decompose vectors and we deal with the same things that we have been dealing since the statics. Triangles, find the components of vectors in different directions, and then use those to find the unknowns that we're looking for. All right, you'll see in examples. So we need to define coordinate frames, right? We need two coordinate frames, one global coordinate frame that is fixed, and one local coordinate frame that is basically moving with the rigid body that we are studying. All right, and in so many cases, I'll mention later on that where to put the frame and what to study, using which point to study, is going to be what you need to figure out. All right, so we define two coordinate frames. Coordinate frames. I'll call the first one global, right? And this is fixed. Right? It's fixed somewhere. Put it on some fixed place. And in so many cases, you don't even need to figure that out. Just think about it as some coordinate frame somewhere that is fixed. And then the important one is the local coordinate frame that is moving, or most of the time is moving. So here is the general form. I say this is the global coordinate frame. Let me put it here so I have more room there. Go X and Y. I'll just represent that with uppercase X, uppercase Y. Then we have our local frame. And let me just put it in some random direction. And I'll show that with X and Y. And call the origin of this frame B, and we can, that's pretty much it. Now this frame, imagine that is attached to your rigid body, moving in the plane, right? If your rigid body is moving in the plane, you have this frame attached to it. It goes wherever your rigid body goes. You'll see it can, so the origin can be attached to it, or your rigid body can rotate with respect to it, but it goes with your rigid body. So either your rigid body, it rotates with your rigid body, or your rigid body can rotate with respect to your frame. Right? It still goes everywhere with it, but there is rotation, the possible rotation about the axis of your local frame. So the global frame is XY, your local frame is XY. Right? So I'm going to study a point. Right? Let's say this is point A on the rigid body. This is point A. Here is a bunch of vectors I defined. The position of the origin of your local frame. I'll call this RB. The position of the origin of the position of point A in your local frame. And we simply refer to it as R A in B, right? Position of point A in frame B with respect to point B, which is the origin of local frame, or in so many cases we just refer to it as R. This is easier. Right? If you eliminate global frame in your local frame, you can think about it, rotation over the fixed axis, right? This is your local frame. There is a rotation any point on this at the distance R, right? And let's also define this vector, which is the position of this point in your global frame, RA, or absolute position, as we call it. And in general form, your local frame can rotate about its axis by angular velocity omega. All right, so we have the global frame, local frame. We are looking at point A. And point A has some position in your local frame, has some position in your global frame. These are vectors. This is our vector, and this is also a vector. This is this setup. This is global. Global frame, and this is local frame. All right. Now, in terms of vector, if you look at RA, RB, RA with respect to B, or simply just R, you can write R. I'm gonna write it. I already put which one is local, which one is global. So let me put it here. We can say RA, or position of A in global frame, is equal to RB, position of the origin of the local frame in global frame, plus RA with respect R in B, or simply just R. If you want to replace that, you can just say R. All right? That triangle RA is equal to RB plus RA in B. All right? That's a simple vector sum, summation of two vectors, RB and RA with in B. Like, no argument about that, hopefully. Now let me put a couple of things here. A, because later on this can be confusing, so it's good to have them all here. A is a point that we are studying. B is the origin of your local frame. Is the origin of local frame. RA is the position of point A. We can write position of A in global frame. RB is the position of local frame's origin in global frame. Position of B, which we represented with B in global frame. What else we have there? We have RA in B, which is the position of point A in local frame. Position of A in local frame. We also have omega, which is the angular velocity of your the angular velocity of local frame about about B, about its origin. So angular velocity of local frame about its origin B. All right. So now this is the relationship between physicians. Now let's take a look at the relationship between velocities. If you take derivative, I won't go into details. If you take derivative with respect to time from this vector relationship, you'll get VA is equal to VB plus V relative, I'll tell you what that is, plus omega cross R. That's the cross product I was talking about. So this is the position. This is the important equation for the velocity that we're going to work with. Now, let's define terms again. Just make sure that things don't get. VA would be the absolute velocity of point A, right? What is the velocity of A? In a sense, whatever we have been studying so far, and we're following a point. What is the velocity of that point? Because we always so far have always had that global frame, right? The global frame was somewhere. We were putting frame somewhere. We're studying the motion with respect to that, right? We're finding ij components along x-axis and along y-axis. That was always this is something we have had so far. Global frame. Local frame is something we're adding to this story. Right? So VA would be the velocity of point A, right? But I'll just put absolute velocity to emphasize that the velocity in global frame. Absolute velocity of point A. VB is the velocity of point B, which is the origin of local frame. Right? Again, absolute velocity. We can think of point B as a point that, whatever point that we've been studying so far. What is its velocity? Right? That would be VB. So again, absolute velocity of point B. You can think of that velocity of point B in global frame. But in global frame means absolute velocity. New things that we see here. V relative. I can't write V relative properly. V relative is the velocity of A, of point A, in local frame, right? We'll see how do we deal with that, but forget about everything else that's happening in this picture with these frames. Now you are just assuming that you have the local frame, the gray frame, and what is the velocity of A in this frame? You don't care about everything else happening. All your focus is on local frame and point A in that local frame. What is the velocity of A with respect to this local frame or in this local frame? That would be your relative, V relative. So velocity of point A in local frame. And can add only exists if A moves with respect to B. What do I mean by that? If this is your rigid body and there is a point A here and this is your frame, if this does not move, if that doesn't move with respect to this frame, either its rotation or its translation, if there is no such motion, either translation or rotation, there is no V relative, right? If everything is, this is frame, local frame, and this is your rigid body, everything moves together, then there is no relative, there is no velocity. The point, all the points on this rigid body, they have no velocity in this local frame. Everything local frame and rigid body moves together. But if this moves, somehow translate or rotates, right? We'll talk about rotation later on separately, but this is the general form of the equation. Depends on how you attach your frame. These things become more clear when we go over examples. But if there is a relative velocity, well, this is not zero. But if there is no motion, well, the points on this rigid body do not move with respect to this local frame, then that's zero. And that goes back to how you attach your frame. Two decisions you have to make: where to put it and what you need to attach it to, or maybe third decision. Third one, what point to study using that frame. But the last term is omega cross R. And that's always perpendicular to R. Right? Just one thing you need to know. Omega is the angular velocity of, as we define that, angular velocity of a local frame about its origin, if it's rotating or not. And R is the distance of the point in that local frame to the origin of the local frame. That's RA in where R is located, A is located in local frame. That's basically R. So let me just add it here. Always perpendicular. This is important because we have to, these are all vectors, so we get two equations. Always perpendicular to R. Right? It's always perpendicular to R. Now, I'll put a note here and we go over examples on C. And they are all vectors. This equation here, just pay attention that V is a vector, so it has a magnitude and a direction. V, A, V, B, V relative, omega cross R. They all are vectors, so they all have, each component has a direction and a magnitude. So they all are vectors and have directions and magnitude. All right, so I'll put it here. All right. Now the equation is straightforward. This VA is equal to VB plus V relative plus omega cross R. Now, how do we implement it? As I said, there are a couple of things that you have to make decisions about. Where to put the frame, local frame, We are not concerned about global frame. Global frame is just a fixed frame that is somewhere, fixed, and it's there. Where to put the frame, which part of the system you attach the frame to, and then what point you want to study using that frame that you attach to. Basically, where B should be, which part of this system of rigid bodies B has to be attached to, and which point we have to take as point A. All right. Let's look at an example, or we'll go over a couple of examples, one today and a couple on Thursday, so things might hopefully get more clear. Let's go with something straightforward, I think. Let's go with, let's see if I can find the figure here on my computer. Let's go with this. All right. It's easier to explain these on figure 5.1. This one. Right. So in this example, we have example. And here I specifically emphasize this is, it has to be X and Y. This is the global frame, right? So you have a sense of where global frame is. Still X, Y. Now, we know this is basically a rod attached to point A. This is a simple rotation about the fixed axis, right? We are just solving this using what we introduced here, because rotation about the fixed axis is an exceptional case for general planar motion, right? So we should be able to get what we usually get using rotation about the fixed axis. It's a good start to just get a sense of how does this, how this is more general compared to rotation over the fixed axis. Because we got rid of one of the constraints that were basically rotating over the fixed axis. Now the question is pretty straightforward. Determine the component of, or we have to say it this way, determine the, what should I say? Determine the X and determine the components of velocity of point A along X and Y axis. Right. Let's see how can we solve this. This is relatively straightforward using rotation of the fixed axis, right? This is point A. You have omega, rotation is happening about O. This is the direction, so you can find VA in this direction. You can find VA in this direction. Right. And then to find the components along X and Y, you can just decompose it and say this is going to be your VAX and this is going to be your VAY. If you decompose it along X and Y, this is going to be your VAY. That you can easily do. And the velocity is R omega. So you have R2 times omega 5 is 10, and then find the components, finding the angles, 30 degrees. You can find 30, 30-degree angle, you can decompose it and find the components of velocity along each axis. But you want to use this equation, right? General planar motion. So as I said, a few decisions you have to make. You have to decide where to put your local frame, what you want to attach it to, right? And which point you want to study. Now, in this case, it's pretty straightforward. Probably you're going to study point A, but sometimes it's not. Well, the next example, probably I'll do in next class. So I'll go one by one. I have to decide where to put my local frame. Now, point O seems to be very promising, right? I can either put it like this along my global frame. Nobody is telling me this is not allowed. Or I can do it this way. I take X along the bar and Y in this direction. All right. So I'm putting the origin, which I referred to it as B previously, right, here. So that's the point that I want to put my, it seems like that's the best place to put it. Now, the second decision would be either this way or this way. Are you going, which part of the system you're going to attach it to? Are you going to attach it to the base here, this, or you're going to attach it to the bar? And that matters, which components of the general equation you're going to end up having, right? So if I attach it, let's solve it first this way, then I'll solve it the other way. Let's say I put it here, X and Y, and I attach it to the bar. So it's attached to the bar, right? If when bar rotates, this axis goes with it. If it wasn't attached to the bar, then the bar would have rotated without this axis rotating. So now it's attached to the bar. And I'm studying point A, obviously. So 3 decisions I made. Now, VA, velocity of A, is equal to velocity of the origin. In this case, my origin is O. VO plus V relative plus omega cross O. VA, I don't know. That's what I want to find out. Now, remember, these are vectors. So they have magnitudes and directions, which means at the end, you're going to get 2 sets of equations, one in I direction, one in J direction, right? VO, well, VO velocity, the absolute velocity of O, right? If O is here, this is rotation. O is not going anywhere, right? So there is no velocity for O. O is fixed, right? It just rotates about its origin. So the local frame, the origin of the local frame is not moving anywhere. It doesn't have any velocity in global frame. So this is 0. If I attach the frame this way, I attach to the bar, and just keep in mind that those assumptions we made. V relative, velocity of A, what was V relative? Was velocity of point A in local frame. If this is attached to a bar and it rotates with the bar, point A is here. Now, point A is not moving with respect to this local frame. How can you figure out V relative? The easiest way is that imagine that local frame is frozen. In this case, imagine this XY frame that I put there, local frame, is frozen. Does point A, or can point A move if the frame is frozen? Now, since the frame is attached to the bar, if the frame is frozen, the bar is frozen. So point A cannot move. So there is no relative velocity. There is no velocity of A in local frame. That's also 0. Again, how do you figure out V relative? Wherever you put your local frame, assume that it's frozen. It cannot move. Now, if it doesn't move, can the point you're studying move? Or since the frame is attached to the bar, if the frame is frozen, the bar is frozen, so point A cannot go anywhere. Point A cannot move, right, without frame moving, local frame moving. So if the frame, so there is no relative motion between A and the frame. If you could if you freeze this local frame and point A can still move in the system, you can still move it. Right? Let's say if point A was attached to another link here, that's a very ugly link, was attached to another link here, right there, and this was point A, then this link probably could rotate, right? So even when you freeze the local frame, point A could move. So there would have been some relative velocity, but let's not just get for now, the general approach, generally, not even for now, always, freeze the local frame and see if, well, whatever is attached to it also should be frozen. See if the point you're studying can move. If it can, you have V relative. If it cannot, you don't. So it's 0 here. So only thing left is omega cross r. What was omega cross r? Omega cross r was angular velocity of the disk the origin of the local frame, omega, that was omega. So if omega is attached to the bar, the frame, the local frame is rotating with omega 5 radian per second. And the distance between the origin and point A was 2 meters. And we said omega cross r is always perpendicular to r, right? And if you can follow, if you use right-hand rule, omega cross r, this becomes your omega cross r. This is your omega cross r, perpendicular to r. This is your r, right? Right. This is your r, and this is omega. Rotation of the local frame. Right? So basically, it becomes VA is equal to omega cross r. Now, omega cross r is perpendicular to r. Since we're doing a scalar approach, we know the magnitude. All we have to do is to find the components along x and y. Right? These are the components. So this becomes whatever is the magnitude of this. I'll write it like this: r omega. That would be the magnitude. And we have the components. So you have to decompose it in x direction, VAX, right? Or better to say omega cross r in x direction, omega cross r in y direction, if you want to think about it this way. And since this is 30 degrees, this is 30 degrees, so that'll become minus sine 30 degrees I plus cosine 30 degrees J. Right? It's upward and it's negative. So VA becomes R is 2, omega is 5 radian per second, and then minus 30 degrees I plus cosine 30 degrees J. And from there you can find your VA. Right? It's 10 times sine 30 is half, so minus 5I plus 10 times cosine 30 is square root of 2 over 2 of, I don't know what it becomes. It becomes 8.66 J meter per second. Could have easily do this with axis about the fixed rotation, but you get the same thing. Now let's do it quickly the other way. Let's go with, I just wanted to show you that you get the same thing as long as you follow the right approach, right? Let's say I attach the frame here. Local frame, X and Y. And this is my frame is here and is attached to the base, right? So now you have your frame here. It's not attached to your bar. Your frame is here, local frame. This is just, and the bar rotates, right? And you're studying point A. See what happens with this approach. You have VA is equal to VO plus V relative plus omega cross R. We still don't know with VA, velocity of point A. Now, VO, the origin of the local frame is still not moving, right? It's just right there. You have this rotation, but your local frame is not moving, it's not going anywhere. So VO is 0 still. V relative. Now, you freeze your local frame. This is your local frame. Freeze it. You have this bar rotating, right? If you freeze it, because the bar is attached to the base, because the frame, local frame is attached to the base, your bar can still rotate. So there is a relative motion between point A and your frame, right? So this is not 0 anymore. We have it. We'll look into it. And then you have omega cross R. Omega is the angular rotation of your local frame. Local frame is not rotating anymore. It's fixed and attached to the base, right? While this bar is rotating, your local frame is not rotating. 3 decisions: where to put the frame, what to attach it to, what point to study. We put it on point A, but we attached it to the base in this orientation, and then we're studying point A. So your frame is not rotating anymore. This is 0. So VA is now equal to V relative. Now, what is V relative? V relative, it's a redundant way of solving this, but I just want to show you that this is the same process as long as equation is the same, as long as you figure out parameters correctly. V relative is the velocity of A in local frame. That's pretty much what we found before. This is the velocity here. Now, the only difference is that now your V relative, you can look at it as rotation about a fixed point. Right? This is fixed. So your V relative is rotation about a fixed point. Fixed axis, what we learned before. So that becomes R omega again. It's 2 times 5 is 10. So you have it as 10, the same story. Now this is a vector, so this becomes magnitude of V relative multiplied by minus sine 30 degrees I plus cosine 30 degrees J. So we'll get, this is 30 degrees, you'll get the same thing. This becomes 2 times 5 is 10 times minus sine 30 degrees I plus cosine 30 degrees J, and that'll give you the same, minus 5I plus 8.66 J meter per second. All right. We'll look at a couple more examples in the next class, but this is all we have. The rest is just figuring out where to put the frame, what to attach it to, what point to study, and make sure that we identify these terms correctly. All right. All right, folks. Let me just stop here.